This is part 2 of a series of videos that will cover decision trees. In this video, we will begin the implementation of the CART decision tree algorithm in Python from scratch. Hi, my name is Michael, and I run a blog called Inside Learning Machines, where I cover topics in data science and machine learning. My aim in this blog is to dive into machine learning algorithms and explain how they actually work. You can find a link to my blog in the description below. In part 1, we gained a general intuition for decision trees and described them mathematically. If you haven't seen that video yet, I recommend that you check that out to have a better understanding for what will be covered here in this video. I have a link to that original video in the description below. For part 2, we will work through the beginning of the model implementation in Python. More specifically, all the functionality that is general to decision trees and not necessarily dependent on whether we are dealing with a classification or regression problem will be coded here. Okay, so here we are in our notebook. I've included in the description below a link to this notebook on my GitHub, so you can go view the complete content there. So the first thing we're going to do is run the cell with the imports of all the packages we will need for both this video and also parts 3 and 4 of this series. So I'm just going to go ahead and run that. So the design here is going to follow an object-oriented approach. So we're going to have a series of classes that will build upon each other until we have a complete implementation of a decision tree. So the first class we're going to have here is called node. And this is just going to encapsulate all the behavior we want to have for an individual node within our tree. So the first function we have here is just our initializer, and we're just going to set up all the parameters for a given node. And you can see here I'm just initializing everything to none. Now this function here is called setParams, and what we're doing here is we are taking in the split point and the feature with which we will divide up the incoming data to this particular node. So in effect, these are the model parameters of the tree, and we store them within this class. So we store those within split and feature here. And if we remember from the previous video, these were called F star. So F star is our feature, and XF star is the split point for that feature. And so each node is going to have these parameters within it, and this is what we use in order to divide up our data and determine whether we are moving in a left or right direction as we traverse the tree. So the next function is getParams, and that is just returning the stored split point and feature for this particular node. So it just returns a tuple with both of these values. Next, we have setChildren. So if we have, or if we're treating this particular node as an interior node, it will have both a left and right child node. And so here we take in two node objects. So here we have left and right, and they're both nodes, and we set those here to these values. So this is how any given node will be aware of what its children nodes are. Next, we have getLeftNode, and this just returns the left node to this particular node that we're at, so the left child node. And conversely, we have getRightNode, and this returns the right child node to this particular node in the tree. Okay, so we can go and just run the cell for node. And now the next class that we will talk about is this one called DecisionTree. Now DecisionTree will be an abstract class, meaning that it will not contain a full implementation of a decision tree. We can tell that because here it inherits from this Python object that I imported called ABC. Now this means that we can't actually use decision tree directly on its own because it will not be fully defined. Now the reason why I am designing it this way is because we saw in the previous video that there's actually quite a lot of logic that is common to both the classification and regression algorithms. And so it doesn't make sense to have to write out all that logic or to code all that logic 2 times for both cases. So instead what I'm going to do is write it once in DecisionTree, and then I will define 2 classes afterwards that will inherit from this class, and that way they will bring in all the functionality that we will cover now. So it's just a nice way of putting all the common logic into one place. So we can start by just covering the initializer function. And so here I define some of the hyperparameters for our implementation. So what I'm defining here is the max depth. This is the maximum number of levels within our tree. So that's just an integer value. And here we have min sample split. And so this is another integer value, and this just defines the minimum number of samples at any given node that are required in order to split that node. So we just store those internally to the instance, and we also initialize this parameter, which we'll cover later. It's just called tree. So the first thing we're going to do is define our abstract methods, and this is what makes DecisionTree an abstract class, is the fact that it has these abstract methods. Now you'll notice that both impurity and leaf value are not actually implemented at all. We just have pass in them both. Now the reason for this is because we saw previously in the first video that the impurity functions and the way that we calculate the leaf values do depend on whether we're dealing with a classification or regression problem. So we can't actually implement these here. And so we have these decorators, just abstract method, that tells Python that these functions will be implemented later in a subclass to DecisionTree. So the first function that we are going to implement here is grow. And grow is a private function that will recursively work through each node in the tree and determine the model parameters. So that's our feature and split point for each given node. And also if we are at a leaf node, it will determine what that leaf value is. So we start by first checking if we're in a leaf node. So these just return Boolean values. And here I'm just comparing our hyperparameters with the level in the tree that we're in. So this is just the depth. This is an integer value specifying the depth in the tree that this particular node is at. And then I also look at I compare the minimum sample split with the number of samples in D in the data that's arrived at this point. I also check to see how many unique labels we have at this given point. And so if all the samples that arrive in D have the same labels, then there's no sense in doing any splitting. This is just a leaf node. So I do all these logical checks, and if in fact it turns out that no, we're good to check for or to do a split, then we fall into this block of logic here, which will then attempt to compute a split point for our input data. So I am going to cycle through all the possible features, f, and their associated split points, so each unique value for the feature f here, and we're just going to cycle through them very mechanically, just in 2 for loops. I then split the input data into left and right parts, and then I calculate the impurity here. And so if you remember, what I'm calculating is this function here. This is the impurity that we saw in the previous video. Okay, and so then, yeah, the impurity is stored in IP. And if IP is less than the previous minimum value computed, then we store that. I also store that if this is the very first IP that has been computed. So if we're in the first iteration in these for loops. So that's just this check here on none. So in this way, we cycle through everything, and we always store the feature, the split point for the feature, and then also along with that, the data that we've split, or the way that it has been split. We store these whenever we have a new minimum for IP. So now when we work through these for loops, we have our model parameters, and we can now set those to the node. So remember, this node here is an input to the function. So we can just specify the split point and the feature to this node. I then can declare the child nodes. So I just initialize those. I call it left node and right node, and then set them to the current input node. So that's just the linking to be able to traverse the tree later. And then I call this function again twice. So I call grow again twice, but now on the child nodes. You can see that's what I'm doing here. And I send in now the split data, so left D and right D, as well as I increment this integer level, which just tells the function at what level in the tree we're at. Now, once we hit a leaf node, we are going to bypass all that code that's just through the if statement that's above. And instead, I arrive here at the else, and we just work out the leaf value, store that to the node, and then return. Now, sort of in the same light, to traverse a trained tree later, we can make use of this private recursive function called traverse. Now, traverse, like grow, takes in as an input value the node, and we also take in an array of the predictor features as well, or a single row of them, at least here. So the first thing that we do here is I'm going to check if we have arrived at a leaf node. If we haven't, we then proceed to extract out the model parameters from the node. So that's the split point and the feature. And then I work out whether we are going to go to the left-hand child node or the right-hand child node for this particular input data, so for X row. So we just do this comparison based on the stored feature and split point, so the stored model parameters. And based on that, so if it works out that we're going left, then it returns this call to traverse, which goes to the left child node. Otherwise, we go to the right child node. Now, if it works out that we are in fact at a leaf node, then all I do is just return the leaf value that's stored within node itself. So now the actual public functions, train and predict, are rather simple. Train itself is the main function, or it's the orchestrator function that we're going to use in order to train our decision tree. So it takes in as input an array of predictor features, that's xn, and their associated labels, yn. So the first thing we do in this function is we join these two together in order to create this array D. I then initialize our tree, and we just do that by setting the root node. We just set it to that member variable that we defined in the initializer, that's tree. And then we just build the tree by calling grow. So I just pass in the root node, the full data set, and then I specify that we're at level 1. So that's just the initial level. And then once this finishes, then we will have a complete trained tree that we can call through self-tree. Now, to generate predictions, we will call predict. And predict has as input this array xn. So this is just an array of predictor features. And so what we're going to do is iterate through each row in xn. So that's what we're doing here with this for loop. And I just make a call for every single row. I call traverse, and I pass in the tree. So I pass in the tree, I pass in the particular row of xn that we want to check, and then the resulting prediction gets stored in this list called P. And finally, I return this in the form of a NumPy array. And that implements all the logic that we want to have within this abstract DecisionTree class. In parts 3 and 4 of this series, I will extend on the work covered here to implement complete classification and regression decision trees. I will also test out those implementations to make sure that they are working as expected. Stay tuned to make sure you don't miss out on that content. If you enjoyed this content, please like the video or subscribe to the channel. If you would like to learn more about decision trees and machine learning in general, please visit my site insidelearningmachines.com. I have included a link to my article on decision trees in the description below. Have a great day, and see you in the next video.